Assalamu alaikum, everyone, or good afternoon or morning, wherever you are. Let me start first by, again, thanking the organizers, especially Dr. Muhammad, on the kind invitation and their commendable efforts to the service and the service to the chemical community. It's a pleasure to participate in this webinar and this conference preceding the largest LLM hackathon for chemistry. And before I begin, allow me to briefly introduce myself. I'm Dr. Alshehri, an assistant professor at Kingside University. I just started this August after completing my PhD at Cornell University, where I specialize in the same area reflected in the name of my lab, AI for Chemia, or the artificial intelligence for chemical, environmental, and material informatics and analytics. You might have noticed a minor shift in the title of my talk. That is from the schedule, from leveraging LLMs to advanced lifecycle assessments to process systems engineering, which wasn't updated in the schedule, but LCA will be covered in this talk as well, and the content hopefully will still be very interesting to you. What I would like to start with is to introduce fairly basic information from the history to the main concept of process systems engineering. Process systems engineering as a term or as a discipline of chemical engineering was first coined in Japan in 1982. And although most of the core concepts have been part of the chemical engineering or the engineering disciplines for quite some time. According to the father of BSc and the professor of chemical engineering at Imperial College London, Professor Roger Sargent, BSc is all about the development of systematic techniques for process modeling, design, and control. And this is to develop an integrated multi-scale system that can deal with the multi-level structure of chemical production systems, starting from the molecular level to the plant and the enterprise level. And overall, this discipline leverages systems engineering and systems thinking to streamline and innovate in chemical engineering and chemistry as well. So there's also an ontological aspect to BSc or process systems engineering. That is, we try to model what exists and what makes up reality. Any whole process can be comprised of multiple components, which in turn can be seen as whole processes on their own, or even at a smaller scale, they may have internal processes and so on. At the end, we find ourselves with process systems or subsystems that interact with each other, and we try to understand their behavior by modeling them, their behavior as well as their interactions with each other. There are also multiple layers to these subsystems or supersystems, superstructures, in a way that they have the physical system itself. When you model it, we consider handling the data, the sensors, the applications, as well as the operations, and even going as far as the business side of processes. So AI in general is not really new to BSc. This discipline, researchers and practitioners have always sought to leverage a smarter way to understand these systems and their interactions. The first phase was sparked by the 1982 paper by the MIT professor, George Stephanopoulos, and was focused on expert systems that aid in decision-making by decomposition methods. That is to find patterns or structures that's consistent with the current data to guide future actions. The second phase was what we call predictive machine learning. from 95 to 2015, where researchers here applied classical machine learning methods like support vector machines and shallow neural networks to process control and QSPRs, or quantitative structure property relationships, for the most part. The third, or the current phase, is generative AI, or LLMs, which also represent the current grand challenge for science and engineering at large. And in all of these 40 years, AI wasn't really that impactful to the field of BSc. So we need to, before we develop new applications of AI in BSc, we need to ask ourselves, what's different now, right now? So as you all know, compute has changed radically, and GPUs used in AI are growing at a faster rate than CPUs, where GPUs computing power is growing or doubling every 6 months. The CPU power is doubling every 2 years. But what's really important is that the price of GPU compute is halved every year to 20 or 2.5 years. That is, just to give you a quick example, training GPT-3 costed OpenAI about $5 million in 2020. And if we were to repeat the same experiment in 2025, that would cost anywhere from $150K or $150,000 to $1 million. However, it is really important, or equally important, to recognize that while the cost is expected to significantly drop down in the next few years, there are also other limitations on the scaling of LLMs beyond computing power, with the most significant being data. So to continue scaling to 2030 alone, we need 80,000 times a larger data set, which is not really conceivable unless we use some data synthesis techniques, which LLMs, or current LLMs, are not really great at. So the next question is, why is this really important to BSc right now? So BSc researchers have always been reductionists, trying to simplify process systems to the most important parts, or isolated systems that they always assume to give rise to the entire phenomena or the system behavior. But that's not always accurate. With this type of compute that we're currently witnessing, we can go from reductionism to systems thinking, where we can move from modeling parts of the system to modeling the system as a whole. We can go from isolation to navigating relationships, connections, and emergence. In terms of chemical processes, we can couple the molecular level with the overall process system's behavior, instead of simply using linear relationships to model their interaction, or dealing with them disjunctively. So in this talk, I'll give more focus on the areas that we covered in our recent review paper, Gen AI and Process Systems Engineering, the Next Frontier, which would include the design aspects of PSC that incorporate molecular product and process designs. It also includes optimization, which involves navigating uncertainties, approximations, and methodologies. Process control, which includes modeling, sensing technologies, and fault detection. And finally, life cycle assessment, or any type of environmental assessment aiming for the quantification of impacts. So as I see it, the challenge of using LLMs in BSc lies in how we can convert or convey these multi-scale systems using language to give us new molecules, to give us new products and processes and action towards the optimal planning and operations and design of chemical processes using only language to represent the complexity of this or such complex systems. This is also an intrinsic challenge to autoregressive large language models, in which using words only or tokens may never approximate human understanding. Critical investigation of LLMs in psychology and in computer science have found that major flaws in their in how they plan or how they dissociate thoughts from actions or logical reasoning. So these challenges have constrained the applications or the current applications or the frontiers of BSC applications and LLMs to unimodal ones that use only language to perform design tasks like featurizing molecules and their inverse design, also generating contextual optimization models and mathematical reasoning. In control and operation, we also see that they are used to contextualize as well states and embed them and take actions accordingly. In environmental analysis, they're mainly used to extract data and operate on them using other libraries or just using platforms that connect them to Python or any other language to do the processing and estimate impacts and give feedback. And the next slides, I'll go over some of these examples that are not my works to derive insights about the future of LLMs in BSc. So in molecular design, there are LLMs are actually at quite an advantage because of the presence of text-based representations like smiles or selfies or the other representations that that have text-based representation. So a great investigation by a paper of one of the earlier speakers, Kevin Jablonka, has attempted to test the limit of LLMs in molecular design and classification and regression and inverse design with some interesting findings. They found that LLMs can excel in regression and classification tasks somehow, but and somehow they also even exceed classical machine learning methods like random forest. But however, in inverse design, they found as long as they tune in or they amp up the creativity or the novelty scale or the temperature, LLMs tend to generate invalid smiles, unlike VAEs or reinforcement learning methods that can generate 100% valid smiles. Other examples in molecular design have also applied LLMs to featurize molecules or materials and yield some improvements in featurization and feature selection over just using the molecular structure or the material structure as a feature. With their average improvement roughly hovers around 10%, which is quite significant. So for process design or the entire process flowsheet design, LLMs have not been applied yet, but some approaches leverages other generative AI methods like generative reinforcement learning and autoregressive methods, which is the underlying mechanism in LLMs. But there's one example here that for process improvement, where the authors found that GPT-4 can improve chemical flow sheets and perform decent reasoning in the unit and operation space. It was shown that it can improve conversion, operation conditions, process feasibility, and techno-economics. So moving on to the role of LLMs in optimization, where it's a similar domain to mathematical reasoning, which has been widely investigated by the computer science community in the literature. One of the significant papers in this domain came out last month and concluded that the current LLMs are not capable of genuine logical reasoning. Instead, they try or attempt to replicate the reasoning steps that they observe in the training period or the training data. These results are based on grade school math, so it's highly likely to be worse for complex representations of mathematical systems and process systems. At the same time, and paradoxically, LLMs have been reported to find new heuristics or search algorithms that improve on current baselines. So we may have to look into the underlying theories and proofs of what we have and instruct LLMs to generate on such grounds. So how this is useful to process systems engineering is a fair question. The answer is that we always make mathematical models and always in them make mathematical and logical errors. One of the foundational books in optimization has 40 plus errors compiled by the authors and also by the readers. And many papers in the field also receive corrections, criticism over formulation errors or practical limitations in the real world. It is likely that we will not realize the full potential of LLMs and optimization through feeding problem statements alone, like this paper has done. They feed the problem statement and they want the canonical form of the optimization problem to be at the output, and they observe an accuracy of 63%, which is quite impressive, but not there yet. And also it's not really applicable to process systems engineering. These are simpler problems and they tend to be just linear problems, not mixed integer linear program or integer program that's more complex. But we also can build more sophisticated systems than what these authors suggested to enhance some of the formulations that we already have from the wealth of literature that we have in BSc to improve and innovate in optimization models and algorithms. So in process control, LLMs are it's performing an even more complex task that is a combination of modeling and optimization. But surprisingly, LLMs have been reported to improve the teachability and control of robots and achieve up to 89% success rate. And the more they tend to have or be more sample efficient than other methods that suggested to teach robots. But when applied to a small HVAC system, they do not perform as well as model predictive control or reinforcement learning. But still, as you may see in the graphs up there, that LLMs outperform random policies and also provide some decent control over, or some decent control better than a random policy, or even GPT random policy is very close to the performance of model predictive control and PPO, which is proximal policy optimization. So it's likely that there is some hybrid model that would enhance model predictive control with LLMs. And as I see it, LLMs and environmental assessments hold the greatest potential in BSc, where we also have laid out such potential in a recent perspective paper by Brice et al. And that's because these environmental assessments have subsystems that can typically decompose without affecting each other. That is, they have sequential steps where we can, for example, define the scope and then extract relational data from the text to build the life cycle inventory and so on. So we can use some type of LLMs or general LLMs here to perform some aspects of life cycle assessment. Early implementations of LLMs and LCA or environmental assessments have shown that they can reduce the time used to perform the impact assessment from days to minutes. But their accuracy is still far from the expert level assessment. So they have roughly 40% error in comparison to the expert level assessment of product carbon footprint. And the method is called auto PCF. So overall, it's hard to represent all the complexities that we take for granted in the real world, that we do not even really imagine that they require intelligence. That is, we keep hitting the old Marvick paradox that state easy tasks for humans are difficult for AI or computers and vice versa. As an example of that, it is really difficult for AI or LLMs to define smells or describe smells, or even pick a screw, or for robots to just pick a screw from a box. There's no reality for LLMs beyond tokens. There's no memory, there's no planning or mathematical reasoning. They seem to just, as we discussed before, that they echo what they have seen. So this makes the data also a limitation, or the modality of the data a limitation. Although you may argue that it would require or take a human 117,000 years to read an LLM data set, but we live in a multimodal world where a human child by the age of 4 will have seen 50 times as much data as the largest LLM. So as I see it, multimodality is the path forward to make LLMs more useful for scientific and engineering domains at large. Although the mechanism that they're using currently is simply tokenizing images, tokenizing videos and audio. In BSE, that can look like encoding graphs or molecules, products, and processes as graphs to reflect how they are represented in the real world and also avoid reductionism. So some final thoughts about LLMs. They're still unideal and quite uncontrollable. That's because of their autoregressive mechanism, where the probability of generating the correct token diverges exponentially with the length of the answer. And as suggested by one of the fathers of modern deep learning, Yann LeCun, a major redesign is needed. So until then, we have to go back to the common aphorism in statistics and in systems engineering that all models are wrong, including LLMs, but some are useful. So let's make them useful. This brings me to the end. Thank you very much. And I'm happy to discuss any views or ideas now.